All right. So guys, do you guys want to like come down, make it a little more intimate? Come on, don't be shy. It's a small enough room that we can make this more of like an interactive discussion, so it'll be more fun. So let's get started. So my name's Jared. I work at VMware, and I work in a group called the Cloud Native Apps Business Unit. And you know, some of you, I think the most common question I get like at our booth is like, why the heck is VMware here? Well, it turns out that like we've actually made a pretty sizable investment in Kubernetes and containers and pods, and really trying to figure out how we leverage a lot of the stuff we do to help operations teams run data centers, and how we can bring that kind of technology into the world of Kubernetes. So from a technology and product standpoint, that's a lot of our mission. But also, you know, part of this group is making a huge investment in open source. And so I know what you may be thinking going into this, like, oh, this is like proprietary software. But you know, the vast majority of the things I'm going to talk about today are either open source or free. Some of them are commercial products, and I'll try to point those out. But there's some pretty cool technologies that you can go download off GitHub and play with today. So I'll try to make sure it's clear where those things are. The other thing is like I deal well with interruption. So you know, feel free to like raise your hand and ask questions in the middle of this. Like I said, it's more fun if it's an interactive discussion. Although you know, if we start to have too many questions, I might ask to hold them to the end. So with that, let's get into it. So the topic here is Kubernetes as a service. And you know, so when we walk around and we talk to organizations, like we have a kind of different perspective than a lot of the you know, other talks here. You know, we're typically not talking at VMware to the engineering team that's building software applications. Instead, we're talking to like the IT and operations teams that have to maintain all the hardware infrastructure and services that go and support those development teams. And you know, we get this question a lot from IT administrators of, you know, how do I actually deliver Kubernetes to my development teams? I've got, you know, a dozen teams inside my business that are asking for a technology like Kubernetes in order to, you know, build their next generation of applications. And, you know, I've got my developers over here asking for this. I've got racks of servers and storage and networking over here. And I have to figure out, like, how do I get from a rack of hardware to actually delivering Kubernetes? Now, if I'm in the public cloud, there's a lot of great options, right? Like, you know, GKE in particular sort of set a bar in our mind for, you know, a great developer experience of actually getting access to on-demand Kubernetes clusters. You can spin them up, you can scale them up or down, you can get them on the fly, and you really don't have to do a lot of administration. But the story is kind of different if you're doing this inside of your own data center, right? So, you know, when we go and talk to people, we see a couple things. Like first of all, there's no integrated solution for doing this. Like Kubernetes itself is a great piece of software, but it requires the bare minimum, you know, a Linux operating system on a bunch of hosts, a networking fabric and a storage fabric underpinning it in order to be able to do this. And you know, so we see people try to take you know, technology like OpenStack and deploy like a private cloud infrastructure on top of that, and then try to deploy Kubernetes on top of that. And all of these cases, we find this becomes a significant integration effort. You know, there's an integration effort both at the sort of OpenStack layer, like getting an OpenStack environment up and running can be challenging in and of itself. And then as you go and actually try to run Kubernetes on top of that, you're looking at like, okay, how am I binding like Kubernetes networking abstractions into my underlying cloud platform? You know, how am I integrating persistent volumes into my underlying storage fabric? You know, how am I going to do authentication and security and authorization into this environment? You know, and these are like pretty substantial undertakings. You know, the patterns we've seen, ironically, is that like when you look at organizations that have actually been successful doing this on their own facilities, it typically involves one of a couple things. It either involves hiring a systems integrator to come in and actually build all this out. And that's often like, you know, a year of work of like customizing a private cloud distribution, figuring out how to bind Kubernetes or whatever container technology you're trying to run to that. You know, so that's like expensive and time consuming. The other path we see people go down is to like actually go hire the committers to these projects. And I'm not talking about just Kubernetes, I'm talking about OpenStack and Cinder and Neutron and like all the underlying cloud platforms. And yet, you know, when we do see people that have actually built this out in their own data center, it often like fails to live up to the kind of experience that our developers are used to from the public cloud. So in terms of like ease of use and integration and degree of automated delivery of that service. So, with that in mind, we built this product called Photon Platform. Right, so Photon Platform is a enterprise cloud infrastructure platform that you can run in your own data center. It's open source, so you can go to GitHub, you can pull down Photon Controller, and I'll talk more about the components of this solution as we go through the next couple slides. But it's basically like it integrates concepts of infrastructure as a service, private cloud architecture, but it's also delivering things like container platforms as a service on top of it. So, with the recent release of Photon version 1.1, we now have a Kubernetes as a service module inside of that. So I'm not going to spend a ton of time talking about Photon. I want to get into the challenges we faced of like what's actually involved in delivering Kubernetes as a service. But it's kind of hard to separate this from the Photon platform. So I'll kind of have to talk a little bit about what Photon platform is in order to describe how we solve some of these challenges. So, walking through this stack, like Photon, first of all, this is a thing you deploy on bare metal. So you take a bunch of servers. We run ESXi, which is VMware's hypervisor. And obviously that is not a piece of open source software. However, you can download a free version of ESXi from our website, and Photon actually works fine with the free ESXi. We also have integrated NSX and vSAN. These are not open source, and they're not free products either, but they're sort of optional components in this architecture, so you can use this without those things. We've actually built our own Linux distribution, Photon OS, which we can use as a guest inside of there, which becomes our container runtime and our sort of default Linux OS, although like any virtualization or cloud platform, we can use any operating system. So if you want to use Core OS, or you want to run Windows, or you want to run whatever, you can do that instead. Photon Controller then is the control plane on top of this. And the purpose of this whole platform is to deliver API-driven services that can be consumed by development teams. So it's kind of like the public cloud experience of getting compute, network, storage, clusters on demand. Now, as we look at actually building this out, there's kind of two sets of users of this platform that have very different needs. So as an infrastructure operator, I actually own the physical hardware, the computers, the power, the storage, the networking gear that actually makes up my data center. And I typically have organized this into racks and pods and availability zones and regions, depending on how large scale I'm actually operating. And so what we do with Photon is, first of all, we virtualize all these things. So we virtualize the compute, network, and storage layers of this physical hardware so that we can programmatically create virtual networks, virtual storage, and virtual compute nodes. What we then do is we layer on top of that underlying virtualization capability a distributed control plane. And so the control plane is basically a set of software that makes all of those individual hypervisors, network switches, and storage arrays appear to be a single system. And the control plane extends a set of RESTful APIs that allow clients to actually consume this infrastructure. And so as an infrastructure operator, my job is to actually operate this platform. So I'm running the hardware. I'm managing the software bits running on all these bare metal machines. And really, through this platform, I'm managing the set of services that a development team is actually able to consume off of this infrastructure. Now, the consumers of this infrastructure are the application developers. So, within an enterprise, we have many different engineering teams that are trying to consume it. You might have, your engineering team, your marketing team might be running ad campaigns that's using compute capacity. You might have a data team that's running analytics, right? And so your job, like as an infrastructure administrator, you're both like operating this hardware, but your job is really like your customer are these different groups inside the enterprise. And you got to think about like, how do I secure each of those groups? How do I make sure they can get the resources they need, that they don't overextend their consumption of the infrastructure? Like, how do I limit, my big data team is always like trampling all over all my web workloads. So how do I like stop them from, using too much capacity from the underlying architecture? And so really the Photon platform is part of it is a technology, but part of it's also like a mechanism for collaboration. It's a mechanism for enabling this sort of service delivery model from my infrastructure team to my application team and giving them a great experience, but allowing the operations team to manage consumption of that compute infrastructure. So I'll start off with talking about this control plane. So there's probably like a whole other presentation we could do just on this control plane technology. So what we have built in the underlying technology of Photon is this software framework called Xenon. So this is open source. You can go to GitHub /VMware/Xenon. And Xenon is a decentralized control plane fabric. It's nothing unique to clouds or containers or Kubernetes. It's, it's sort of a marrying of a database-like transaction processing system and an application server. And what it lets me do is basically create like a set of RESTful resource objects that have like JSON documents behind them. So like an example would be like a VM or a network segment or a volume. Each one of these things is represented by a JSON document with some RESTful URI. And what Xenon does is, first of all, it lets me establish a ring. So I run a bunch of these Xenon fabric nodes. They end up forming a ring and distributing all of these JSON objects and control processes across that ring. It uses an asynchronous programming model. So like it's kind of like a database in that it stores these JSON objects for you. However, it's also a programming model. And you actually write little service controllers associated with every namespace in the control plane fabric that allows you to add logic. So in other words, like this system, like I can not only post a JSON object representing a VM, there's also a program that runs that handles inserts, updates, and deletes of VM objects. And I can compose these things into larger systems. So I can create like a JSON object that represents, say, a Kubernetes cluster. And when I create one of these, the service handler for it is going to call back into the control plane to create VMs and networks and disks. Those things have service controllers that handle those creation events and talk to the underlying hypervisors. So this in and of itself is kind of an interesting system. It's in many ways it's a database. It uses view stamped replication. It's distributed, so as I add more nodes, it actually partitions by data so that each node actually owns a subset of the data. It's able to do tunable consistency, so we can get quorum reads and writes, or you can do optimistic reads and writes. It facilitates things like leader election, and it actually includes a Lucene-based full text index over all the data. So all of these objects inside the control plane, like VMs, networks, disks, and things that we're managing, there's actually a pretty expressive query language that lets you, write queries against your data center to say, like, find me all of the network segments that were created by, Bob on Thursday that have more than this many IP addresses allocated to them. Like you can write sort of pretty expressive things like that. And it's actually packaged as an embeddable Java runtime. So unlike, in many ways it's similar to something like etcd in that like you run a bunch of them and you store data in it. However, instead of running it as a separate process, it's actually a thing that you link in to a Java program. And so your binary becomes the actual store and node process that runs that makes up this thing. So like I said, there's a whole other presentation that we could do on Xenon. I'm not going to do that today. So when we actually go and run this, when you look at like what's inside this control plane node, so first of all, we are the compute fabric. So we can't presume that there exists a computer before we actually do our work. So the way this works is you actually start off with your hardware, you install ESX onto a bunch of machines, and then you starting these Photon controller guest processes or VMs on these underlying hypervisors. So a standard production deployment would be 3 nodes because it's a quorum consensus system. So you want to be able to, if you want to be able to survive a single failure, you have to run at least 3. But you could run 11 or 100 depending on how big your data center is. And what's going on inside of these control plane nodes is there's a bunch of microservices backed by REST APIs that do a bunch of things. Yeah, question. Good question. The question was, do all the nodes run control plane components or just a few? The answer is just a few. So, like I said, standard deployment model would be take a bunch of ESX hosts. You would run 3 control plane guests on 3 of the VMs. Those things network together, form your control plane. You could run on more, but best practice is not all of them. So inside of this thing, there's a bunch of services. So first of all, there's this thing called the API front end, and this basically facilitates like, a REST request can arrive at any node in the control plane, and that will handle forwarding that request to the node that actually owns the object you're trying to talk to. There's things like the housekeeper. This is like a garbage collector for your data center. So it like detects things that are not being used by any resources anymore and will freeze those resources. The deployer handles things like migrations and updates to the control plane itself. There's a scheduler that handles placement scheduling of VMs, storage volumes, networks, things like that. And we have Cloud Store, which is kind of the database of inventory of all the stuff running inside of here. And those control plane processes interact with a guest agent that runs on the ESX host itself, called the Photon controller agent. And so what that agent does is things like when I schedule a VM, the control plane is going to pick a host and say, like, you're the one that's going to start this VM. The Photon controller agent on that hypervisor is responsible for interacting with the actual hypervisor kernel to say, start this VM locally. So what you end up with, and what Photon actually delivers, is this model where I can take this pool of infrastructure and I can carve it up into multiple tenants. And then each of those tenants can start creating resources. And resources might be virtual machines. We can create Kubernetes clusters, which are really just aggregates of VMs, networks, and disks. We also support things like Pivotal Cloud Foundry. And this allows you to share a single pool of infrastructure to support multiple tenants running many workloads on top of the same infrastructure. And it gives your operations teams the ability to sort of manage how that access is actually happening. So with that, let's dig into like what's actually involved in Kubernetes as a service, and particularly what we see from an enterprise perspective of what goes on here. So there's sort of a lot of different problems to be solved to deliver Kubernetes as a service. Some of them are technical, some of them are not. So for example, the first one, commercial support, right? One of the things we found is that, whatever solution you're choosing, what our customers found was that they had to piece together, storage vendor X, network vendor Y, operating system vendor, Kubernetes vendor, all these different things. So one of the problems we solved is actually giving a completely commercially supported stack. So I think part of the news here is that when you use Photon platform commercially, we actually, at VMware, will take a call with any problem related to anything from the hypervisor, the Linux kernel, the Kubernetes distribution, the cloud control plane, any of the components involved. The next thing is like, how do you actually provide like an on-demand self-service interface? Right, so developers want to get a Kubernetes cluster on demand. It needs to be like an easy-to-use interface. You can't ask them to specify 20,000 lines of chef templates to do that. Those things have to spin up fast and be responsive in order for it to really be useful. You have to solve problems of resource management, right? How do I carve up the available CPU, RAM, and disk inside the data center to allocate it to different teams? I need to be able to do things like network microsegmentation. So, the idea that my data center is one gigantic, network address space, and that everything can see everything else, is not really a great idea for a lockdown, enterprise, highly secure environment. So customers want to be able to do things like carve up, at a minimum level of by tenant. So each cluster could get its own isolated address space. But we've actually taken that a bit further and able to dive deeper into the Kubernetes cluster itself in order to segment networks. You also do storage management, right? So Kubernetes has persistent volumes, but those volumes all are represented by actual volumes on disk somewhere that we need to manage all that state. Finally, we have multiple tenants, right? So how do you actually administer granting somebody access to the system? What happens when somebody gets fired and you got to remove their access from the system, and how do you audit access and things like that? Another question. I think the question was, is the storage management vSAN or any data store?
That's the question.
All right. Who wants to be the holder of the mic? All right. Thank you. The storage management can actually use any vSphere data store. Hey, show of hands, how many of you guys are familiar with vSphere? Okay. So it's probably about half the room. So vSphere has this model of data stores. A data store is just a thing that can manufacture volumes for applications to use. So vSAN is a thing that can be a data store vSAN can be a data store for vSphere or for Photon platform. In other words, vSAN basically is software that aggregates all of the disks on all of the hosts in your Photon cluster. virtualizes them, lets you dynamically create volumes. There are other things that can be data stores for Photon as well. If you have like an NFS filer, that can be a data store. If you have a fiber channel storage array, that can be a data store. So you don't have to use vSAN, but vSAN is a supported option. So start off with the basics. So dynamic provisioning. So the basic interaction here is obviously relatively simple to imagine from a user experience, but you've got some developer who wants to go create a new cluster. So we're presuming they already have access to Photon. They've already got the command line tools installed and an account provision. And so basically the workflow here is the developer says like, hey, Photon, create me a Kubernetes cluster. Now, Photon actually knows what a Kubernetes cluster looks like. So what's happening inside the control plane is the control plane is actually creating a new cluster object, and a whole bunch of stuff is going on. It's like a big Plinko machine inside the control plane where it's like creating VMs and disks and etcd nodes and API masters and actually provisioning all the underlying virtual resources to run this cluster. Once you've actually created a Kubernetes cluster, the developer can actually use kubectl to talk directly to the cluster. So we don't sit in the path of that cluster once it's created. We're just involved in actually provisioning it and setting it up. But we don't stop there, right? So, one of the things we see in a lot of existing techniques for provisioning clusters is that the IaaS is kind of dumb. Like, it doesn't know that this set of 20 VMs is a Kubernetes cluster. It just knows that you created 20 VMs. So Photon works different. So Photon actually knows that there's a Kubernetes cluster and that these are the VMs that make it up. And it also knows what a healthy Kubernetes cluster looks like. So while Kubernetes can handle, like, if a kubelet node goes away, Kubernetes is going to reschedule all the pods that were running there. But there's nothing inside of Kubernetes that's actually going to replace that node in the Kubernetes cluster itself. And this is where Photon Controller takes over. So what goes on is, first of all, the control plane of Kubernetes, of Photon, actually knows about this Kubernetes cluster, and it's health checking the underlying infrastructure. So it's making sure that the networks we created still exist, that the VMs and all the nodes that we created, that the etcd nodes are still there, that the API masters are still there, and it's making sure that they're all healthy. And so in the event that one of the nodes in a Kubernetes cluster dies, first of all, Kubernetes is going to reschedule the pods that were there. But the control plane of Photon is going to know that minion has gone away, and it actually automatically replaces that node and rejoins it to the cluster. So these types of operations, like the loss of any of the VMs or networks or disks that make up your Kubernetes cluster, like these will all be automatically corrected by the Photon control plane without, in most cases, without any human intervention. So this like right out of the gate like eliminates a lot of the actual administrative load on an operations team for managing Kubernetes. Now, we can also use this capability to do dynamic scaling. So you can imagine that your developer is like using a 20-node Kubernetes cluster. Maybe they're getting ready for an ad campaign or something and want to scale up double the size of the cluster and the capacity. So what they can do is they can actually ask the control plane to resize the cluster. So where I had like a 20-node cluster, they might say, hey, change that to a 40-node cluster. So what the control plane can do, because we know about the existing Kubernetes cluster and its existing configuration, we can actually go spin up a whole bunch of new Kubernetes nodes and then join those nodes to the existing cluster. Right? So we don't need to tear anything down in order to start up a bigger one. We can do this as a no downtime resize of the cluster. And just to give you a feel of like what this feels like to use, I've got a little recorded demo. It's hard to give a live demo of this because we have to like ship a rack. So this is the developer portal. So when you log in, like when you use Photon as a consumption, as like a developer using this thing, you've got a web UI, there's a CLI, and there's a REST API. Obviously, the web UI is the easiest thing to show. But what we're looking at here is we have a tenant view. So this is like the marketing team's view. My view is broken down into projects. And then projects are the things that own like VMs and clusters, et cetera. I can see up at the top of the screen, I've got the, I can see my quota of like how much CPU, memory, disk capacity I'm actually allocated and how much of that I'm actually using. And so what we're going to do is we're going to click into one of these projects. You can see that there's already 3 Kubernetes clusters. And what's interesting here is that there's a huge sort of consolidation of the cognitive load of looking at my data center because these clusters might have like dozens of actual VMs and networks and disks. But as a consumer, I don't actually need to be aware of any of those individual VMs. Like the system knows that those VMs are there, but as a consumer, I'm just looking at Kubernetes cluster 1, Kubernetes cluster 2, Kubernetes cluster 3. And then I can, go through here and create a new one. I just have to give it a name. I tell it I want a Kubernetes cluster. We do support other types of clusters besides Kubernetes. I have to configure some network settings, like I can assign different, DNS servers to different Kubernetes clusters. I can give them different address ranges. I have to give it some information about, like, what size should each of the nodes be? Should they be 16 CPUs or 8 CPUs? And it's showing me here, allowing me to choose the size of my cluster, and showing me the impact on my actual quota of like how much of my allocation of data center capacity. Now, once I've done that, the system's actually, now it's off and actually provisioning that cluster. It's got to create the VMs, it's got to launch the kubelet software on those nodes, it's got to start the API masters and things. Here I've got a view of, I've clicked into one of these clusters and I can see all of the individual VMs that make up this particular Kubernetes cluster. So again, the control plane knows about what all the components are that make up a cluster. So now once I have a running cluster, we're shipping basically off-the-shelf Kubernetes software. So we have not like forked Kubernetes and made our own custom distribution of it. We're shipping upstream Kubernetes, but we're also shipping all the same software that you get if you were to download and use Kubernetes itself. So from this UI, we can actually click through right into the Kubernetes management user interface. I'll talk in a bit about how we do single sign-on, but basically all these things share the same user credentials and access privileges. And now once I've set up the cluster, the process of actually deploying a pod or a service is just done exactly the same way I would do if I had set up Kubernetes myself. So this thing, there's like uploading a YAML file, deploy some pods. And again, we didn't build any of this software, which you're looking at now. This is all just like the management UI that comes with Kubernetes. So, this kind of like shows the user experience of actually consuming a Kubernetes cluster. But in a moment, we're going to flip over and look at what an administrator sees that's actually managing this cluster. And I might skip my. All right, yeah, he's resizing it. Okay, so if I'm an administrator, I get a view more like this, where I can see all the different tenants. I can create new tenants, so maybe I want to create an account for my marketing team, and I can grant user access to individuals. Now, Photon actually integrates with my corporate directory and single sign-on. So you can, when you deploy Photon, you can actually connect it to like Active Directory, or if you have like an LDAP directory, or SAML or OAuth. And we can reuse all of that authentication and authorization logic inside of this cluster. So when I create a tenant, like for my marketing team, I don't need to create like user accounts for every person on my marketing team. Like that's managed in the corporate directory, whatever I'm using centrally to manage logins for like email and log into your laptop and all that stuff. We just reuse all that infrastructure. What I'm doing as an administrator is I'm basically managing these tenants and managing the resource allocation to the different tenants, as well as taking on basically the hardware lifecycle management. So like dealing with maintaining the machines, doing patching and upgrades, dealing with outages and stuff like that. Okay, so let's talk a bit about resource reservations. So the problem is like, how do I actually allocate resource? There's a question there. Yeah, the question is like cluster upgrade. How do you actually do that? So there is not actually a cluster upgrade a feature in Photon right now. I think that in our view, a lot of that stuff, I think that there are things that are being handled in the lifecycle SIG of Kubernetes itself, of like how to actually do a Kubernetes live upgrade, and we would basically reuse that work inside of this platform. Yes, the question is, are you stuck with whatever version of Kubernetes? So the system can actually support multiple versions of Kubernetes simultaneously. So user 1 might have Kubernetes 1.3, and user 2 might have Kubernetes 1.4. So when you're creating a new cluster, you can actually create a new version. You can deploy it with a new version of Kubernetes. So what you can do today, if you download the software, is like, if Kubernetes 1.5 comes out and you're running 1.4, you can create a new 1.5 cluster, and then you could basically do a migration of your workloads out of the old cluster into the new one. And then as the upgrade process of Kubernetes gets more feature-rich, we would be able to do an in-place upgrade. Our target is to be able to do an in-place upgrade, but it's just not built right now. So from a resource allocation standpoint, right, I've got lots of different resources that are, I need to share. I need to share CPU, RAM, storage. So we have this concept of what we call resource tickets. And a resource ticket is basically like an allocation of capacity to a team. And, we saw this in the view earlier. So what I can do is that I can create multiple resource tickets. I can assign them to a team. And it basically is just like specifies like how many CPUs, how much memory, how much storage is this tenant allowed to use. Those things are all additive. So I can create a new resource ticket and grant it to a team to give them more capacity. And that basically sets up a quota of how much aggregate CPU, RAM, and storage capacity a team can use. And that's shared across like whether I'm using Kubernetes or just straight VMs or running Cloud Foundry. All of that is the same shared pool of resources. So the next piece is networking, right? So, and we have a sort of unique problem here because we need to handle networking not just from Kubernetes, but also for the broader data center control plane. So, a bit of a roadmap here. So today, if you pull down Photon and deploy it, what you're actually getting is the flannel overlay network. Which is the same thing you'd get if you just used kubeadm or whatever mechanism to deploy it. But our NSX team has been doing a lot of very cool integrations with Kubernetes, which will be available very soon. I'll talk about some of those things. So first of all, I'm going to assume you guys, we're at KubeCon, so the Kubernetes flannel overlay, this isn't news. We didn't do anything new here. This is the off-the-shelf software. But what we're doing, it's kind of an eye chart. So what we've done is we've integrated NSX with Kubernetes. So with NSX, there's a couple of things to understand. So first of all, our view of the infrastructure is, we look at the hypervisor itself, and then we have to look at the guests running inside that hypervisor, and then we have to look at the pods running inside of those guests. And so with the NSX networking model for Kubernetes pods, you basically have we do an IP address per pod. And there's an OVS, an Open vSwitch, running in each minion VM. And so basically what happens is that OVS running in the minion handles all the actual pod traffic from that minion and handles basically relaying that to another OVS switch or switch that's running in the hypervisor itself. So the hypervisor basically is like aggregating the traffic from all the minions. The minions are aggregating the traffic from all the pods. But all this acts as like an integrated network fabric. So we're able to do, container interfaces per pod and per container inside of that. We can do a distributed firewall that runs essentially inside the hypervisor. And this basically allows us to implement firewall rules and security rules that execute in a distributed fabric across all the hosts. So you don't have to, if you want to do firewalls, say to protect two pods from each other, you don't have to send all that traffic up to some central firewall to get filtered and then back out to the other pod. Instead, those firewall rules and those security rules get pushed down out to the edges in all the individual hosts. And in essence, every container and every pod has a little virtual firewall that's sitting in front of it that's managing all the traffic in and out of it. Running short on time, so I'm going to skip over some of the details here. But this is some very cool stuff. The second thing is that, so NSX actually manages the networking layer both for pods and VMs, but it also has done a deep level of integration with Kubernetes itself. So within Kubernetes, the default networking model is flat, right? So the entire Kubernetes cluster, every node needs to be able to talk to each other, every pod needs to be able to talk to each other. But for a highly secure environment, this often isn't good enough. So what we've done is we've actually integrated NSX Control Plane with the Kubernetes control plane in order to synchronize the network segmentation with the underlying Kubernetes configuration. So the way this works right now is we actually basically watch the set of namespaces that have been created inside the Kubernetes cluster and create network segments inside of NSX for each namespace. So every namespace in Kubernetes translates to a separate isolated network at the virtual networking layer. And this means that, first of all, two namespaces don't even have addressability to each other, so they can't talk to each other unless you create a route between those namespaces. But we also added the ability to do security groups through NSX that apply to all the pods running inside of these namespaces. So the way this works is that I can say this pods with this tag are able to talk to pods with this tag, and when I go deploy like a pod spec, I can actually include labels that are understood by NSX and control that distributed firewall. So basically, in the pod spec that the developers are actually deploying, that can tie that pod into the security rules that have been defined by the network administrator. And I'm looking at the guy who wrote all this to make sure he's nodding at me, saying I'm describing it right. He's nodding, so I'm good. So this is very cool. Basically, we're able to do very tight security on all of the traffic between pods inside this cluster, and give, from an administrative view, you can create corporate-wide policies, like these people are allowed to talk to this database, and everyone else is not allowed to, or these systems are allowed to talk to each other, or these are not. And you can actually centrally administer that, and you can administer it not only within the Kubernetes cluster, but also across Kubernetes clusters, and between Kubernetes clusters and non-Kubernetes infrastructure running on Photon. Yeah, question. Is the question, did I go to the talk about Calico?
So I was just saying that it's not the implementation of Calico. The concept of microsegmentation predates Calico. I mean, it's existed a long time before that. The idea is very simple. Wherever your workload goes, your firewall policy follows it. It makes it very easy to manage your firewall policies. So NSX had this technology for a long time. We've been doing it for virtual machines. We've just extended it to containers too. The added difference between other solutions is that we don't try to apply the firewall policies just below the pod inside the VMs. We don't think it is secure. If you assume containers are not secure, then your firewall policies just below a pod is not going to be secure. So we keep all the policies inside the hypervisor so that even if there's a container breakout, your firewall policies, they just cannot touch it. So that's the point.
So the next area that I'm going to talk about is storage management. So this stuff is coming soon to some degree in Photon, but I'm going to talk about the bulk of the work here actually happened in the upstream Kubernetes repo, specifically for vSphere. But so basically, when we talk about storage for Kubernetes, you've got these persistent volumes and persistent volume claims, and your underlying infrastructure has to provide something that provides that persistent volume capability. So what our storage team has done is actually done an integration of basically vSphere storage primitives into Kubernetes. And you can actually see this in the Kubernetes project. There's a getting started guide for how to run Kubernetes on vSphere. The code base is actually in the cloud provider interface in Kubernetes itself. So the bulk of the work is actually in there. The thing that changes when we move to Photon is there's slightly different APIs for Photon compared with the vSphere, but most of the work has actually been done. But basically what this allows us to do is we can use the underlying storage fabric of vSAN or any data store to create volumes. Those volumes become persistent volumes as far as Kubernetes is concerned. So I can, as a storage administrator, I'm using vSAN to manage all of these volumes in the pool of storage that I've got, and then I'm exposing that to the developers of Kubernetes so you can create different flavors of persistent volumes. So when we say flavors, we have a feature inside of our software called storage policy-based management. So a storage policy allows me to define like data protection rules, quality of service rules. Like I can define whether or not I want this data duplicated or not. I can define whether I want it encrypted or not. And so I can create storage flavors as administrator. So I can say like this is an encrypted, highly available, RAID 5 array with this like QoS setting on the storage fabric. And I'm going to call this like disk flavor high performance. Right? And then as a developer, I can create a persistent volume of flavor high performance, and I'm going to get that storage policy applied to that volume. That manifests itself to the developers, just different types of persistent volumes they can create, but it manifests itself to the operator as essentially the management of the storage array, of servicing the actual underlying disks that may fail over the course of the day, of expanding capacity and looking at utilization and things like this. So again, this stuff is coming soon to Photon, but you can get a feel for what this whole system looks like by playing with the vSphere integration with Kubernetes that's in Kubernetes today. So the next piece is on multi-tenancy. Right? So there's a underlying identity model inside of Photon where we create tenants. Tenants can create multiple projects. Projects can contain multiple Kubernetes clusters. Projects can also contain things like virtual machines and Cloud Foundry clusters and other things that aren't Kubernetes. Tenants are isolated from each other at a compute layer by the hypervisor. So my Kubernetes nodes and your Kubernetes nodes are completely separate virtual machines. They're also isolated at the network layer. So like my Kubernetes cluster and your Kubernetes cluster are different networks. And we can extend like even within the namespaces in those clusters are different networks. But we also have this centralized identity management model inside of here. And so the way this works is that there's actually an identity directory inside of Photon platform which handles all of the authentication, authorization, and access control across the cluster. So this is based on an open source project called Lightwave. Lightwave is basically at its core an implementation of an identity directory using LDAP, but it's also an OAuth server, it's a SAML server, it's a certificate authority, and implements a whole bunch of different protocols for sharing that identity and access management data across different things. Lightwave also allows me to federate with my corporate directory. So I can actually add Lightwave essentially to a Active Directory federation in a one-way trust relationship. And that allows me to reuse all of the identity data that's already in my Active Directory in order to provide access to Photon. So when I create tenants, I can actually bind tenants to different trees in my corporate identity directory. And I can actually bind different tenants to different directories. So I might actually have completely different identity directories for different tenants. And I can manage all of that centrally through this system. Now, what's interesting is that this means that I can basically use my corporate credentials to log into Photon. But it also means that we can actually integrate the authentication authorization provider of Kubernetes with this identity directory as well. So for example, there is an OAuth provider inside Lightwave. And what we're working on right now is we're actually activating the OAuth authorization plugin inside of Kubernetes so that when I create a Kubernetes cluster, it basically inherits the authentication and authorization rules of the project in which it was created. So if I have a project and I want to give 5 people access to it, I give them access to the project, I create the Kubernetes cluster, and anybody that has access to the project will be able to perform API commands against the Kubernetes cluster. If I remove you from the project, not only can you no longer talk to Photon, but you also can't talk to the Kubernetes cluster anymore either. Again, remember, putting this in context, our goal is to make sure that like for the developers up at the top, that if I'm a member of like tenant B, I'm able to perform API commands against those 2 Kubernetes clusters, but I'm unable to talk to any of the other tenants working on that same platform. So, just in the nick of time, we got to the end. So I said, a lot of these things are open source. A lot of the technology we talked about today are up on GitHub. Photon controller is the underlying control plane, totally open source. You can go to GitHub, VMware, Photon controller. Photon OS is our Linux distro. This is what we're running as the node and the underlying Linux OS and all these Kubernetes nodes that we're running. That's also up on GitHub. Lightwave is the identity and directory infrastructure. That's also up on GitHub. You can pull it down. Xenon is the underlying framework. That's the control plane that we built Photon platform on top of. That's also open source and up on GitHub. There's more things up there. But that's all I got today. I think the key thing is I hope was kind of like an interesting journey of looking at, how do you do, a shared infrastructure pool that can support many Kubernetes clusters simultaneously? How do you manage the resource reservations, the network security, storage management, identity and access management, all of which are things that I think need to be provided by the underlying platform in order for Kubernetes to work in an environment like this. And that's all I got. Thanks. Yes?
So the OS was switchable. Do you lose anything by switching out Photon OS with Core OS or parallel OS?
So the question is, do you lose anything by switching out the OS? No, not really. I mean, it behaves a lot like how you'd expect on EC2, right? Where you've got different AMIs. You can launch an Ubuntu AMI or a RHEL AMI. I think when we launch a Kubernetes cluster, the default image that we use is the Photon OS image. And a lot of that was just we had to pick something, and this was an option that was could be included in the platform and could be commercially supported by VMware without having to include any third-party relationships. But we have customers that run RHEL on top of it, that run Core OS on top of it. All those things work great. Any other questions? All right. I'm here if you want to catch me after the talk to ask anything more. Thanks.